Hello everyone, good morning. First of all, I would like to thank the organizers for giving me the opportunity to present my work. So today, I am going to talk to you about two single field model of inflation and one multi-field model of inflation. And since the main topic of this session is volume inflation and string theory, let me slowly take you to the string theory domain. So, inflation, so it is a period of accelerated expansion in the early universe, and I'm going to embed such mechanism in string theory. So, what do I explicitly mean by that is that I'm going to derive the scalar potential driving inflation. I'm going to attribute a physical origin to the scalar potential as well as the scalar fields driving the inflation. So, both the single field models of inflation that I am going to talk about and the multi-field models, all the scalar fields and the scalar potential, they are going to have a physical origin derived from string theory. And my talk is going to be based on these papers and are done in collaboration with these people. Okay, let's begin. So, in my talk, the three papers that I'm going to present, the three works that I'm going to talk about, in all of them, there will be some things that are going to be common, which are the string theory model building, which is telling you that how am I going to derive the scalar potential and what are my scalar fields. More or less, the physical origin to the scalar fields are going to be also the same, but if they differ, I will let you know. And the moduli stabilization, because when I say string theory, usually what comes to the mind immediately is that there will be a lot of scalar fields, right? Because string theory comes with a lot of extra dimension, and once your dimension reduce, you get a plethora of scalar fields. So, you have to stabilize the extra scalar fields. So, I am going to talk about inflations, right? So, my inflation is going to be the leading order flat direction, but the leading order flat direction, but the leading order stabilized directions, they need to be stabilized. They need to be stay stabilized even at the level of 4D, otherwise they will mediate fifth force. So, so when I talk about string theory, I have to let you know what will be my extra dimensional topology, because the derivation of the scalar potential as well as what exactly are the scalar fields, they will depend on this topological structure. So, for my case, this topological structure is a K3 fibered Calabi-Yau, which is nothing but a two-dimensional base, and which is like a disc, and on each point on that disc there is a K3 fibered K3 fibration. So, there is a two complex dimensional manifold sandwiched on this disc. And when I talk about this volume inflation and fiber inflation, they are single field models of inflation, and in those cases for volume inflation, this whole 6-dimensional volume will stretch and expand in the space time and will give us the period of accelerated expansion. When I talk about fiber inflation, this fibration, so this fiber is going to stretch and expand. And when I am going to talk about multi-field inflation, a combination of these scalar fields, so there will be 3 scalar fields that will appear. The combination of them will stretch and expand, and there will be some kind of assisted inflation. So, I haven't checked yet, but maybe the single field models will not work when I talk about multi-field inflation. So, will be an assisted inflationary kind of picture will emerge. Okay, so slow roll inflation in its minimalistic situation is when a scalar field, minimally coupled scalar field, minimally coupled scalar field slowly rolls down a potential, and as soon as it stays in this plateau region, inflation takes place, and once it rolls down, inflation stops, and one usually takes care of all these how long the inflation is taking place by these slow roll parameters, and as soon as they hit 1, inflation stops. But and this is also the we all know this is the Planck contour plots, and all this colored region that you can see, this curves, they are they are based on various single field models of inflation, and we can see that they are well within the Planck window of observation and within the Planck contours. But then why do we need to go beyond that? So, in order to answer that, we need to know that other than particle physics, for cosmology, you should not take gravity as a constant. You should not work on a static gravity domain. So you have to take the dynamics of gravity into picture, and since inflation happens in such a high energy scale, the quantum gravity constraints might also become important. And for string theory being the leading candidate of quantum gravity, we might be interested in working in that domain, and hence the subject string cosmology has emerged, and I'm going to talk about string inflation in that. Okay, and not only that, so string theory naturally features these scalar fields which can drive this accelerated expansion, inflation, and also it can also give rise to dark energy, to quintic scalar. Okay, and many others. So and these are the things that we have to keep in mind. Like, why do we need to go beyond the single field model of inflation and the toy model of inflation? What is the motivation to go beyond? Okay. So now the outline of my talk is the following. So first I would like to search for the de Sitter vacuum, because we know we have to, in cold inflation, we have to reheat the universe. So the field has to go through the oscillation. So we need a de Sitter vacuum to start with, and if found, then I would like to examine what will be the inflationary implications of those vacua that I am going to find. And one thing that I should already tell you is that I am going to talk to you about because I said that I am going to derive the scalar potential, right? So the way I am going to derive the scalar potential are based on only the perturbative corrections from string theory. Because usually, you have, I don't know if you have heard about this LVS and KKLT type construction, which is the famous de Sitter construction found in the literature for string theory vacuum. So now I'm going to go slightly beyond that, and I'm going to just work on perturbative corrections, because perturbative corrections are well understood from the 10D perspective, and non-perturbative effects are not. So it is, I'm going to claim that it is better than the LVS and the KKLT scenarios that were studied earlier. Okay, so this is a busy slide, but the takeaway from this slide is the following. So I'm going to, I'm talking about superstring theory, right? So I'm starting from 10 dimension. I'm dimensionally reducing to 4D. So whatever is happening in my 10D is going to be carried forward to 4D with the help of this standard Guko-Vafa-Witten superpotential and the Kähler potential. And remember that these are tree level. Tree level means this is the simplest interaction that could happen in the Lagrangian, right? So this Guko-Vafa-Witten superpotential, this omega and G3 that we are seeing here, those are actually taking care of all the fluxes that are needed to stabilize this extra scalar fields that I was talking about. And this is also taking care of, this is also carrying the information about the geometry. So, I'm already carrying forward the information from the extra dimension. And the Kähler potential again, but there is a different combination, but the Kähler potential is also taking care of the same thing. So the volume is taking care of like how my geometry is embedded, like whether I am talking about this K3 5 at Calabi-Yau or some torus or whatever. So now, I don't know if you remember that in the start of my talk, I said my inflatants, the inflatants are leading order flat direction. So in this leading, so these are these leading order corrections, right? So in the leading order, just these leading order corrections are not sufficient to stabilize the inflator. And this is helpful in a way that, because since this is leading order flat direction, they are usually less massive and easier to inflate with. Okay, and the main point of this slide is that these two potential, this superpotential and the Kähler potential helps us to derive our scalar potential to drive the inflation. Okay. So I keep talking about inflation because that is the main goal of my talk. But this is just usually used to stabilize the scalar fields as well. So it can be used to do many other things as well. Okay, so now I have to stabilize the inflatants because those are leading order flat directions. So I have to stabilize those flat direction using this set of corrections that I am going to consider. So these are all perturbative corrections. So those perturbative corrections appear in two series in the 10-dimensional string perturbation. So one is in the string length and the other is in the string coupling. Okay. Now, if we add the standard alpha prime cube correction, that is the first leading order corrections in the string length, and the higher derivative corrections, which is the second order string theory corrections, string length correction, then I arrive at this potential, which we have shown. This is the potential which is simpler looking, and it is single field, where my phi is the scalar field, which is also the inflator, and all this constants, they can be written in terms of several other parameters, and I get these questions quite a lot, that it looks like there is a like array of parameters, but it is not so. So once so this W0 and GS are my main free parameters. And once I fix this GS and W0, the other parameters will be based on that. So I cannot choose arbitrary numbers. I cannot just throw arbitrary numbers to them. Okay. So and once we plot this potential, and once in the this is the zoomed in version of the of this side. Yes. Yes. Okay. And we can see that it features a nice flat plateau to sustain inflation, and we have also checked its this is the volume inflation I am showing, and in the volume inflation we have checked the volume. It's a large volume scenario at the end of the day to to keep the perturbative corrections under control. This is a well known things in string theory. And we have also checked the power spectrum, the spectral tilt, spectral index, and one main thing and one beautiful feature of this model is that this volume inflation, this is the first single field model I am showing, is that this is a small field model. Hence, it is okay with the light bound and as well as with the Swampland conjecture, so Swampland distance conjecture to be precise. And so this is the next single field model that I am going to present now, is that this is the fiber inflation, but fiber inflation in using only perturbative corrections. So in this scenario, since we do not have any non-perturbative effects, what beautiful things that it brings is that there is no Kähler cone bound. So usually these fiber inflationary models, they suffer with a problem where the inflaton, how much it can like field excursion is bounded by Kähler cone conditions. But since there is no non-perturbative effects, there is no such bound in this scenario. Since I have only 2 minutes, I will skim through. And again, we have checked the inflationary regime, and we are okay with that. Let me show to you the last model, which is a 3-field model, which was the last work that I have done on this perturbative large volume scenario type situation. Okay, so this is a 3-field model of inflation, and in all the 3 fields, they are the base, the overall volume, and the K3 fiber Calabi-Yau. So in this situation, we have added the log loop correction and the leading order alpha prime cube correction, the log loop correction, and the another leading order subleading order f to the power 4 correction. And we have stabilized all the direction, and this is one of the most important feature is that the second slow roll parameter, there is a violation, there is a brief violation of slow roll, and it returns back to slow roll again. So there is a violation of slow roll, and we can confirm that. So these type of features usually gives rise to an enhancement in the power spectrum, and which might be useful to study the prime order black holes as well as the secondary induced gravitational waves. So there could be interesting features, and not only that, it can also be used to study the non-Gaussianity, because usually we have also checked the turning rate and the torsion in this three-field models of inflation, and usually because of the presence of these turns and torsions, they have non-trivial effect on the non-Gaussianity as well. It has been found. And how long do I have? 1 minute? Okay, 0. Okay, so I'll just stop here. Okay, so yeah, so I'll just stop. I'll just let you read the thing. Thank you.
Thanks, Divya.
Yeah.
Questions?
So in one of the models you showed these parameters which fit the data very well. If you can just go back even more. The previous one. Yeah, this one.
This one.
So you really have to fine tune your model parameters so much to fit the models. So because you have taken so many numbers after.
Yes. Yeah, this is also another question I get very often. So this is what I get after I plug in some value. So this is not the fine tuning. So suppose I give some numbers in the Mathematica, and then the Mathematica gives those the Mathematica gives those orders of magnitude, and I just put it there. So from the next talk onwards, I really should remove those. So I don't need to fine tune that. So suppose there's like this art.
It looks like a very fine tuned.
Yeah. So no, they are not fine tuned. So fine tuning, I will say, so this W0 being 0.038 is fine tuning. I need exactly 0.38. Maybe 3.9 will give something. It will not overshoot my model, but it will give some other prediction. Then my lambda being 10 to the minus 4, this is what I need. And CW being 10 to the minus 5, 10 to the minus 5, this is what I need. The rest of it, what I get from Mathematica, for instance.
Okay.
Yeah.
Any other questions? So I thought the upshot is that if you want to be consistent with the observations, this is the very specific set of parameters that will work with the observations, right?
Yeah.
Which means there's a fine tuning.
So fine tuning in the sense, in the paper, so here I'm just showing, I just picked the best parameters, set of parameters. So in the paper, you have actually given a range of parameters.
Okay.
It's like,
there's a wider range of parameters.
Yeah, there's a wide range of parameters. Yeah. Even in the three-field model, so you can imagine, so even this three-field model, so I'll just answer what I could not say in the talk. So this, this brief violation of scroll is actually occurring because there is a global minimum. And when the three fields are away from that global minimum, the third field, which is like the dominant one during the first period of inflation. So you can see that these are the 1, 2, 3. So these are the three fields where the first field is the most dominant one in the first period of inflation, and the two of them are slowly moving. So when this one is going here and it's slowly oscillating, it's because the two of them are away from the minimum and there is a ridge being formed, and this field which is dominant in the first period, it falls in that ridge and oscillates, and that oscillation actually induces this brief violation of slow roll. And once the other two fields goes close to the global minimum, all of the fields find their global minimum and they go to their global minimum, and it comes back to the normal slow roll, and the inflation ends when all of them are at the minimum. And this feature is retained for a wide range of parameters, but since this is a string theory model, one has to make sure there are various scales and there are various parameters we have to make sure, because there are supergravity approximations, there are various no-go theories.
I think I got your point, yeah.